Right. Good afternoon. Any questions, any comments? Anybody want to say anything? So I want to talk a little bit more about magnetic monopoles. So okay, this is about magnetic monopoles, and if we have time, I want to show something called Dirac quantization. So let's first start with like a recap. So okay, not this one. So what we said is like if like the change, like right, the key idea is like when you have a dynamics in quantum mechanics, if things are time dependent, of course it becomes much more complicated mathematically, but also it's more interesting. And one of the, in my opinion, most interesting outcomes is so-called Bayer phase, which was coming out in the case of like a so-called adiabatic evolution. And what we said is like Hamiltonian depends on a set of parameters, and we show the set with lambda. Of course they depend on time, but not to clutter, we don't show it. And they have so-called instantaneous eigenstates, right? This lambda depends on t, this lambda depends on t, and they have instantaneous En, which also depends on t through lambda, and this is n lambda. Right? And if this is the case, and to compromise between time-dependent Schrödinger equation and time-independent Schrödinger equation, what we said is we had to introduce so-called Bayer phase. What this means is this instantaneous eigenstate at t is equal to 0 will evolve to instantaneous eigenstate at t up to phases, and there are two phases. One is so-called Schrödinger phase, minus I over h bar, from 0 to t. So this is dt prime e n lambda of t prime, right? If e n lambda was time independent, this is our usual Schrödinger phase. And on top of this, so we call it like Schrödinger phase, on top of this we also have this geometric phase or Bayer phase, I gamma n of t, right? And this gamma n of t, after working through time-dependent Schrödinger equation, what we found was something like this: from 0 to t, dt prime n lambda of t prime I d dt prime n lambda of t prime. Good. So this is what we call Bayer phase. And we rewrote this, like we said, okay, this is actually like this thing depends on lambda implicitly, explicitly, not on t explicitly. So we said we can just change this like this. So this is lambda jth comp, right? Lambda is the set, lambda 1, lambda 2, dot, dot, dot. Each one depends on t. And we said this d over dt, I can do the chain rule, d over d lambda j, d lambda j dt. And this is the gradient in the parameter space, lambda space. So we wrote it like this. So this is del, and we remind ourselves this is gradient in the lambda space. And this is a dot product with so-called velocities in the parameter space, and we call this like this. But after this, right? Okay, let me do it like this. So this is d lambda dt. Okay, this is t prime, and we are physicists. We can cancel this, right? We can cancel this with this, and then this is going to be like a line integral from lambda of 0 to lambda of t. Good. And after that, we introduce from here. We introduce so-called Bayer connection, so which is A is equal to minus I. Now I think we understand things depend on parameters, right? And this is just a clutter, it's not helping anymore. We can just hide these parameters and say, that, okay, this is instantaneous eigenstate. There is this gradient in the parameter space, and there is another instantaneous eigenstates. Right? And this is this object which kind of looks like a vector potential from electromagnetic theory is what we call Berry connection. And the problem with Berry connection was not problem, but its property is like if you change n, right? Quantum mechanical states are defined up to a phase with I omega of n. A changes like A plus gradient of this, okay, again in the parameter space, gradient of this phase. So these are phase dependent. And from there, we like motivated. We can define maybe something like electromagnetic tensor Fij. Right? This is by definition del I. Okay, this A is a vector and it has components Ai minus del J Ai, and del I is short for del over del lambda I. Then we showed under this phase redefinition Fij goes to Fij, right? These are, if you want, kind of like electric and magnetic fields. Okay, these were all abstract, and then we said as an example we can consider spin a half, right? Simplest system we use to introduce quantum mechanics. There is nothing simpler than a spin a half system in magnetic field, and Hamiltonian is given by minus B dot sigma. Sigma are Pauli matrices. We found the eigenvectors and eigenvalues, and we put it in this formulation. Okay, maybe I can remind you quickly what this calculation was about too. So we said this B, which is the external magnetic field, we can say its magnitude is fixed, but its direction is changing adiabatically. Then we can put all of these inside this formulation, and what we found is, for example, A, right, is going to have theta and phi components. There are two adiabatic parameters. It's going to be two-dimensional. We found A theta for this one. Okay, this is B is equal to B cosine theta. Sorry, so this is, I think, sine theta. Cosine phi. This is sine theta, sine phi, and cosine theta. Right? We plug in Hamiltonian, we find eigenstates, and then we put those eigenstates in the definition of this A here. Since there are two parameters, there will be two components. We found A theta, which was 0, and we found A phi, which was minus cosine squared theta over 2, and Fij, because there is only theta and phi, and Fij is anti-symmetric, there are only two components, and we call these components F theta phi was found 1/2 sine theta, right? And then after that we said let's look at the integral of this thing in the full parameter space, d theta, d phi, right? This d theta goes from 0 in the north pole to pi in the south pole. So this is 0 to pi. And this phi goes from 0 to 2 pi. And we plugged in f theta phi. Right? This is like a simple elementary integral, and we found, did I find 2 pi? And from there we said, okay, let's remember the Gauss's law. And Gauss's law was what? Gauss's law is like if you have this ds and E, right? This is Q enclosed divided by epsilon 0. Right? For a point charge, just the presence of this integral immediately implies E is 1 over 4 pi epsilon naught. Okay, there's also Q, R divided by R cube, right? By just having Gauss's law, if somebody gives you the Gauss's law, this is enough for us to conclude the monopole, right? And this monopole is electric monopole. Here, the Gauss's law is given to us after all these calculations. From there, we said we can immediately calculate. So this is electric monopole. We can immediately conclude a magnetic monopole because of this. Okay, let me write it like this. Because of this, I can write this as some closed surface integral dotted onto some f, which is related to here, and from here f. So this is in the real space R. This is in the B space, right? B is the parameter. Therefore, the electric field becomes magnetic field in the form like this: B1 over B cube. And we call this magnetic monopole. Right? So this is just a long recap, but now I want to extend the discussion a little bit and show you why this is actually non-trivial, why it's interesting. Any questions? Any comments? Yes.
We do not use any parameterization in the default, right?
We don't use any
parameterization because, for example, if we want to go back to another parameter, for example,
bx, by here.
Yes.
Yes. I mean, you can absolutely do that. Yes, bx, by, bz.
So we can take the line integral. Yes.
Exactly. But it's a little bit harder. Yes.
But we did not, for example, normally the integration part in spherical coordinates are r squared sine theta d theta.
Yes.
But we wrote only d theta d phi. I know we're using two parameters, but what happens to r squared?
Yeah, exactly. So this is right. So this is our okay. So there is like a sphere here, absolutely. So we have like a sphere here, and there is some radius r. And first, right, this is d theta and d phi. There is no r, there is no b here. So because right, we found this result, and we plugged it in here, and that's the result 2 pi. Now what you are saying is like, what about r squared? Right here, there is r squared here. So this one, for example, r squared d cosine theta d phi, and for this to be equal to 2 pi, right? This thing, okay, and also right, there is like radial vector r. This is a vector, a unit vector r, and this should be dotted onto something, and this thing should be what? This thing should be exactly 1 over 2 r. If you want, let's use unit vector r divided by r squared. So that this r squared and this r squared cancel. That's how we deduce f to be a vector like this, yes. But of course here I need to be careful. This is not in the real space, this is in the parameter space. That's why this is b. So this is b squared. So this is b hat, and this is b squared.
Okay, so normally r squared is there, but it cancels out.
Yeah, I used r squared, exactly what you said, to deduce this result.
Okay.
Yes, that's a good point. Thank you. Good. Now, okay, let me remind you something we use all the time in electromagnetic theory. So there's like so-called Stokes theorem. So what this says is like I can have like this. Okay, it's frozen. Okay, I can have this domain of integral, right? And I can do the area integral. Let's say this closed surface, the surface integral dotted onto B, right? This is area times B. This is the flux. I think we call this Ampere's law in 105. Rather than doing this, we can do the following. We can do, rather than area integral, we can do the line integral around the boundary. I think the I use the L. So this is the L. Okay, this B is what? The B is curl A, right? Rather than curl of A, I can put A here. And this is what we call Stokes theorem. Hopefully everybody is familiar with this, right? Trivial now. Now I want to use the Stokes theorem for our result and see there's like some pathologies that we need to iron out. So in spin 1/2 case, this integration domain is what we call two sphere. It's like a sphere, and let me try to draw like a sphere here. And I don't know, on the sphere I start in like some, okay, this is my parameter, and I slowly vary my parameters, and then I come back to myself again, right? I'm completely on sphere and close a loop here, and this is the area I am talking about. And there's like a C, and what is, okay, after doing this full adiabatic evolution, I ask what is the total bare phase I acquire, and I can use our results. So the total bare phase is I times gamma is equal to X, this thing, right? We already derived it here. So I'm going to write it in terms of this A. So this is going to be minus I. This is now line integral. So I use D lambda dotted onto A. And what I want to do is like now I want to use the Stokes theorem here, right? I can copy exactly the same thing, and rather than this line integral, I can do the area integral here, and I can use curl of A to be this little f, or if you want, this is B. And what is S dot F here, right? So that's like let's write in two steps. So this is X minus I, so this is d theta, this is d phi, and this thing we found 1/2 sine theta, 1/2 sine theta, and this right around this loop we now have d theta sine theta d phi. What is this object? There's like a name for this. Solid angle, right? Yeah. So this is what we call solid angle. That's why this entire thing, right? I think there's like some radius. This one? Yeah, I think let me write it like F here, yes. So then this is e to the minus I omega over, because of this 1/2, 2. Good. Okay, the conclusion is the phase I acquire after adiabatic evolution is e to the I gamma is equal to e to the I solid angle. But now there is like a problem, right? On the sphere, I can draw any loop, right? This is my loop. And there is like ambiguity. What is inside and what is outside is ambiguous. What if?
What is the direction of the vector f? Because we didn't specify the outputs.
I think the direction here is always radial, right? I think ds dot f is equal to this based on our identification above. So f, that's why I'm using little f. Little f and uppercase f are different. Last time you need to contract uppercase f with epsilon ijk to get little f, but I don't want to get into the technicality, which is not important. Yeah, it's little f and uppercase f, they are the same thing. You can forget about their difference. But what's important for us is like, right, this thing is area integral, and area integral is this thing, which is what we obtained.
How are they the same thing? Because the F, the capital letter F is derivative, the little f is the monopole expression.
They are the same thing up to like a factor 1/2. At least in 2 dimension, right? The technicality comes from like this Fij is like in arbitrary dimension.
Yes.
In 2 dimension, if you are in the surface of a sphere, they are exactly the same.
Okay.
But in more than 2 dimension, the identification requires a little bit more thought. Okay, now we found this identity. The problem is, so I have a loop, and on a sphere, what is inside and what is outside are ambiguous. Why? Because if you draw this and somebody else comes and says, okay, here's your orientation of loop. So this is your orientation, right? I have right-handed orientation, and this is inside. Somebody else can come and say that, okay, what if my inside is here, right? I can do this perfectly, and there is like a different solid angle here, and we need to make sure this different choice should not cause different results, because we said Berry phase is like something physical. So what I want to, okay, let's think about this case. First, what we need to think about is like total solid angle. What is the total solid angle on a sphere? 4 pi. And let me call this C. So solid angle for, let me call this S. So this is the surface S choice. We found it to be omega. And let's call this surface choice S prime. What is the solid angle for S prime in terms of 4 pi and omega?
4 pi minus.
Exactly, 4 pi minus omega. And now I want to consider this Berry phase for this alternative choice. Let me call this omega prime, right? And from what we found is this is going to be e to the minus I, right? This is now C d lambda dotted onto A. But we don't have to do this integral every time. We did it and we found it. We found it to be e to the minus I omega prime over 2, right? I just copy this result. Okay, this is, let me copy this. This is plus now, right? Based on this identity, I just copy omega prime is going to give us, gamma prime is going to give us omega prime. But this loop, right? This loop here is right-handed. If you want, use right-handed rule and try to enclose inside. Your hand is going to point in one way, but this loop is left-handed because you're right. To cover the outside, you need to switch the direction. That's why we need to put another minus sign here. So this is orientation of the loop. Now let's plug in. So this is equal to e to the minus I 1/2. We found solid angle for this omega prime is 4 pi minus omega, and this is equal to e to the I minus I. 4 pi divided by 2 is 2 pi, and e to the I, minus I, minus is plus, so this is plus 1/2 omega. But if I go back and look at it, it's exactly what I defined, e to the I gamma, right? This is e to the I gamma, and this is 1, and as you can see, this is e to the I gamma, right? So that means I have the same Berry phase for closed loop. And that's what it should be, because we said this bare face should be gauge invariant. If I had like an open loop, that I wouldn't have that. Good. Okay, this was like a long exposition, but now I want to come to electromagnetic theory, and suppose we live in a world with magnetic monopole, and look at it, how it would give us some troubles. Okay, this is now a pause. Now I'm opening a new discussion. Of course, this discussion is going to use this result. Suppose, okay, why don't we have magnetic monopole? For that reason, because B is equal to something like curl. Now I don't have to write this parameter because this is real space. Curl of A is B, and this immediately tells me del dot B is what? 0. And based on this, people think there's no way I can get away with a magnetic monopole, right? Because I need to have something non-zero for having, right? Think about Gauss's law. Del dot E should be rho over epsilon 0. If rho is 0, there is no charge. But let's pause a minute here, and let's suppose there is like a magnetic monopole. If there is a magnetic monopole, we already found it, right? So this B is equal to some charge, magnetic charge, divided by 4 pi. This should be the magnetic field due to magnetic monopole. I just copied the Gauss's law and changed the charge, and that's all I did. Now let's think about this. Let's think about something like Schrödinger equation, but for magnetic monopole. So let's suppose I have this G here. So this is my magnetic monopole, and I put a charge exactly like hydrogen atom. I put like a charge, and this charge is like bound to this magnetic monopole. And I imagine I adiabatically vary the position of this charge and bring it back to where it was. And now this is a little bit additional information from 300, right? If there is, right, magnetic field, and there's like here, right, magnetic field is piercing through this, and as you trap magnetic flux, as you close the loop, what is going to happen? There was like anybody from 300? In quantum mechanics, right? In the quantum mechanical case, suppose I have some magnetic field, and my pad traps this magnetic field. There's another effect. Exactly, right? There is like Aharonov bomb effect, if you remember, and the Aharonov bomb effect is just a phase. So this psi, due to this loop, is going to go to e to the, how did I use it? Let me choose it, I q over h bar loop d l dot a times psi. So this is in the first semester what we called Aharonov bomb phase. But now we know Berry phase, right? There's no difference. So this is exactly the Berry phase in the geometrical approach. So I think if you never saw this, I think you can go to Phys 300. We talk about this for like, I think 2 or 3 lectures at least, and let's not get distracted. Suppose this is given, and then let's see the consequences. Now I want to use the Stokes theorem. Let's use Stokes from here. So this dl dotted onto A is going to be ds dotted onto curl of A, and this is curl of A is, right, this is B, and this is going to be, now I am thinking about So this is equal to G if I enclose all sphere, and this is going to be G times omega over 4 pi if I enclose solid angle omega. And from here we can find what phase is, right? Phase is going to be just, right? Because of this Q over H bar, we have Q over H bar, and everything else is what we had, Q over H bar times G times omega over 4 pi. So this is again bare phase. But now due to magnetic monopole. Good. Okay, I have one last move to make, and then it will be the end of the discussion. But again, right, I have ambiguity. Am I going to enclose here inside, or am I going to enclose outside? And these two ambiguous choices should give the same result. Let's play this game one more time. So e to the I gamma, this is the first choice, should be equal to e to the I gamma prime. This is the second choice. And gamma we just calculated, so this is the gamma. And gamma prime is exactly the same thing, right? But for the other solid angle, and because of orientation, I also have minus sign. And I know from full angle should be 4 pi, gamma prime should be equal to 4 pi minus gamma. Now let's plug everything in and see what happens. So this side, e to the I gamma is going to give e to the I q over h bar g omega over 4 pi should be equal to, so this is e to the, first I plug this in, minus I, right, this minus q over h bar g 1 over 4 pi times 4 pi, and now I'm writing this term e to the I q over h bar g omega over 4 pi. Good. Now this term and this term are exactly the same. That means, okay, this 4 pi and this 4 pi also cancelled. That means, so this thing is 1. And for this to be 1, what do I need? Right, this needs to be 2 pi q over h bar times g should be equal to 2 pi up to an integer, and n can be positive or negative integers. Therefore, we found a quantization condition. So if, okay, conclusion, if there exists a magnetic monopole, that means if G is non-zero, right, then Q is equal to 2 pi h bar, this is 2 pi h bar, divided by G times n, and n is integer, charge is quantized. Okay. Even if I have like a single magnetic monopole, that immediately implies the charge should be quantized, right? And what is this quantization? If you are thinking about electrons and conventional quantum mechanics, you can think about electron charge, right? Plus E or E minus E. And if you are a particle physicist, you have to think about charge of quarks, which is E over 3, but either way, one way or another, all charge, positive or negative, should come in units of this charge quantum. Of course, we said if there is a magnetic mole, there's a quantization, but for many theorists, they think a little bit backwards. Okay, so this is for many theorists' dream, for theorists. Since charge is quantized, right? Charge is quantized, at least empirically. We don't know why, but as far as we know, all the charge we see in nature is quantized. We don't see like fraction of a charge. Charge is quantized. And they use this logic a little bit backwards. Then there should exist magnetic monopole. And of course, there are other reasons for magnetic monopole because they are theoretically very nice, but I think that's the beginning part of the argument. But of course, like we always say, something doesn't exist unless you observe it, right? Because if you are in the mathematics department, that would be fine. In physics department, if you don't see it, it doesn't exist. And so far, we didn't see magnetic monopoles, and there is no reason for us to believe they exist. Any questions? I have a little bit more material, but I think that's at least bare minimum for me. Any comments? Any suggestions? Okay, a little bit, 2 more pages, but this is optional. If you feel like you are with me, we can continue. If you feel like you are losing it, we can stop here. How many people can follow what's going on here? Okay. Okay, let me then highlight one last aspect of this, and then after that I'll finish. How about suppose there is like a magnetic monopole, we still need to get away with this thing, right? So B is equal to curl of A, and no matter what you do, if that's the expression, del dot B should be 0, right? We need to do something about that. Unfortunately, that's not so simple. Let me give you the answer, and if you have the appetite, you can go and read more about this. So the answer, 1A cannot do it, right? 1A, there is no way with like a unique A that's defined globally, you can come up with this. The answer is, you need at least 2 vector potentials to cover a 3D sphere. And let me give you these A's, and then after that I'll finish the discussion. The first A is, I'll call A north. That's well-defined vector potential for the north pole, and its form is something like this. So this is G over 4 pi r, 1 minus cosine theta divided by sine theta, unit vector along phi. Okay. So as an exercise, check del cross A north is B, which is going to be G over 4 pi r hat over r squared. Like you need to look at the curl in spherical coordinates, plug this in, and it's like 2 lines of calculation. But you can see, right, in the north pole, that's well defined. Why? Because sine goes to 0, but 1 minus cosine also goes to 0, and this entire function is regular in the north pole. That's why I call it A north. Whereas if I put theta goes to pi, right? Now numerator is non-zero, but denominator is 0, and I have undefined. So as theta goes to pi, A north is singular. That's why I also need to define a second gauge. So the second gauge is A south. And this goes like this. There's like a minus here and plus there. Now, as you can see, right? Okay, this is south. If I set theta goes to pi, 1, cosine pi is minus 1, this goes to 0. Sine pi goes to 0, 0, 0. This is like a regular function. But theta goes to 0. Now, numerator is finite, but the denominator is 0. This is singular. That's why I call it also check. This also is easy check. Del cross A south is also exactly the same B. Again, you need to use curl from Wikipedia in like spherical coordinates. Therefore, what we have is, okay, we have two spheres, like in one gauge, right? This is what we call it a gauge choice. And in that gauge choice, we have singularity, of course, right? Because of R, we have singularity in origin. And we have singularity in North Pole. In fact, entire line from here is singular. This is what we call flux tube. Sometimes people call this Dirac string. All the flux you want comes from this South Pole and they emanate to the entire sphere. So this is A north, which is regular in the north. The second choice is, where is the flux tube in the second choice? What is the reasonable place for this flux tube to enter? Yeah. So in this case, flux tube or Dirac string enters from north and it emanates the necessary flux. So this is again Dirac. Also, okay, this is also an easy calculation. Maybe I can ask you to do that and then finish it there. Do you have a question?
Will electric potentials be compatible with their...
Exactly. Let me also, I think I skipped that. So, A north, right? They should be compatible. How? The vector potential is not a physical quantity, right? Vector potential, two different vector potentials can agree with each other up to a gauge transformation. And that gauge transformation is something like that. A south plus some overall gradient. And this W is, I just wrote it here. I think I calculated this one. Del W is equal to 2G divided by R sine theta E phi. Yes, right? Because it's not physical, you need to do a gauge transformation from one vector potential to another to see if they are. If you don't have anything like this, you would be right. They would not be compatible. Maybe, okay, let me give you one last exercise and finish it there. This could be a little bit abstract, but these are actually testing your understanding from like vector calculus. Everything you need is like given in like 106, or like if you take calculus, line integrals, surface integrals, that's what you need to know. You can check. Suppose I put like a tiny loop here, like S. Okay, exercise for A south and C, tiny c around North Pole. Calculate this, right? So this is A north dotted onto the R in this tiny loop, and at least what I found here is minus G over 4 pi times 2 pi times 2, which is equal to minus g. And what this means is all flux enter through Dirac string. And if you do exactly the same thing, okay, this is north, okay, this is south. And if you do exactly the same thing for north, okay, this north is regular, right? There is no singularity. If I have like infinitesimal loop here, what is going to happen? What is the total bare phase? Right, this is flux, which is regular, times area, and area goes to 0. Right, it's going to be 0. So this is, also check this is 0. And we know these two agree because we just found this Dirac quantization, and this gamma prime and gamma should be agree up to this solid angle phase. Good? Any questions? Good? Right, thank you.